All right, everyone. What we're going to do in this video is we're going to walk through a screening for regression, but this time we're going to go and do a screening for a moderation analysis where we've got interaction terms involved when we're looking at residuals and leverage values and influence values and things along those lines. So the basic procedure is going to be similar to previous examples we've gone through, just a couple other things that we need to go through and switch up in terms of optimizing this as you're working through things. So the set that we're going to be working with is this exercise moderation 2 set, and the variables that we have, the model that we're going to test here. Similar we've got to some of the previous examples that we've put together. We're going to test a model with 2 interactions. So we've got participant sex, female, male. We've got NOS total. This is an indicator of attitudes towards the utilization of support. So we can have lots and lots of support available to us, but if we have negative perceptions about the utility of utilizing support resources, so if I think that support resources are untrustworthy or not helpful or things along those lines, we might see that impacting different types of functioning, maybe more so than structural support. So our NOS score range 0 to 80. This is going to be attitudes towards whether or not it's helpful to utilize support. And then we have this INQ belonging measure. This is going to be an indicator of feelings of alienation from friends and family, where 0 or 1 is not feeling alienated or disconnected. High levels, 7 being that I don't feel connected or lonely, or I feel high levels of loneliness and alienation here for this. And then our SPSS, this is just perceived social support. Okay, and so what we're interested in looking at in terms of our interactions, we want to know to what extent attitudes towards support utilization influence the association between thwarted belongingness and social support. Okay, so here we're modeling or conceptualizing this as our NOS scores changing the strength or magnitude or direction of the association between belongingness and perceived support. And then our second interaction, does the relation between thwarted belongingness and social support differ for men and women? So here, again, our base relation is belongingness and support, but we're looking at to see whether we have different associations between belongingness and support for both for either men or women. Okay, so these are the models that we're going to go through and run and screen. We're not actually going to go through and look at these models in this video. We're just going to go through and do a screening and cleaning for these data. Okay, so I'm going to start with our data set here. And first thing we want to do is see if we have any missing values. Okay, and so in SPSS, the way I like to do this is just quickly run through and run a sort on your data. So we sort this. Okay, it looks like we've got 2 values here that are missing belongingness scores. So we'll want to go through and I'm going to file, save this as a scrap file, just so we're never modifying our original data set. But I'm going to go through, record missing value for IMQ belonging for cases 216 and 301. Going to get rid of those. Sort, so I've got total NOS scores, and then sort, looks like I'm missing a value for my MSPSS, so my social support measure. So that's case 189. Going to make sure to record that, and then we'll go through and get rid of that case there. Okay, so what I'm left with is a set of, had 223 to begin with. In my reduced set is 220 observations, and so I lost 3 people, just 3 people, due to missing values on the INQ and MSPSS. So want to make sure that we're going through and recording those for our write-up that we'll have to do later. Okay. So now what I'm going to do is I'm going to go through and look at my descriptives. So I'm going to look at distributions for my INQ belonging, my NOS, and my MSPSS. I'm going to save standardized variables, and then options, that happened on my other screen, request skew and kurtosis there. Gonna hit continue, paste, set up my syntax file, and you probably already have one of these that you've been working on before, so you can work from that. But what we're gonna do, gonna go through, take a look at our univariate distributions here, okay? So it looks like all of our values, let's pop this up again, just so we can take a look. For NOS 23 to 66, that fits. INQ belonging 1 to 7, that fits. MSPSS 0 to 7, 1 to 7. So those are all within range. So that's looking good. So we don't have problems with plausibility of values in our continuous scores. Skew, we've got some positive skew, a little bit of positive skew for thwarted belongingness. MSPSS total has some negative skew, but within bounds of what we would generally consider not problematic for these data. Kurtosis, similarly, all less than about 0.7, absolute value 0.7, so no super strong concerns in terms of just our absolute values of our scores in terms of problematic deviations from normality. Okay. Also want to go through, because we have a dichotomous predictor, want to look at frequencies for participant sex. Take a look here. Okay. So we definitely have an unbalanced design. We have twice over again the number of people, the number of women as we have as men in this sample. So we've got about a 3-to-1 ratio of women to men. So we have unbalanced sex variable, but not optimal, but still within the bounds of what would be reasonable in terms of our model. So in terms of our, do our values fall within acceptable range? Yes. Univariate distributions, at least based on our measures of skew and kurtosis, things are looking reasonable at least. Okay. So, but let's go through and graph and take a look and see what we're seeing in terms of our box plots and our histograms. So I'm going to go through, take my 3 continuous variables, dump those into my dependent variable, label cases by my subject ID. Okay. And then for plots, I'm going to request histogram and click off stem and leaf. I'm going to paste that in here, go through, take a look at my histogram. So for thwarted belongingness, I'm seeing some level of positive skew, right? A little bit of positive skew, with most people reporting low levels of alienation, isolation, with sort of as the distribution increases, some higher levels here. But again, maybe noting some of that positive skew, but otherwise doesn't look terrible in terms of our distribution. Our box plot, again, nothing falling beyond 1.5 times in our quartile range, still evidence of some positive skew. We see this is our median value here and our upper whisker at max value, lower whisker at bottom value. So again, still seeing some imbalance in our median based statistics, but nothing that would be concerning there. So our feelings about and perceptions of the utility of support networks have what looks like a pretty nice symmetrical distribution here, things that are approximating normality in terms of the histogram. We've got a value that's scoring quite low, and a couple values scoring high here that are detached, sort of separate from the remainder of the distribution, but overall not looking like it's too terrible. Here, if we're looking at our box plot, same thing. We're seeing looks like 4 cases that are just falling just above 1.5 times the inner quartile range. And that's going to be probably this collection of cases up here. Case number 176, that's falling down here, right? So we might want to note those cases in our screening, but overall, nothing that's looking too concerning. Okay. Then we get our histogram for our measure of perceived social support. Okay. Remember that our MSPSS, this was the value that had the strongest level of negative skew. Still not terrible, but getting close to a skew of -1. And we're kind of seeing that here. Most people reporting relatively high levels of perceived support, and then things trailing off and people reporting relatively low levels down here. Same thing with our box plot. We're seeing evidence of negative skew where we've got our first quartile, our second quartile, third quartile extended down here, with 3 cases looking like they're falling below 1.5 times the interquartile range. So overall, want to go through, describe these plots, and note cases that are kind of falling out of bounds. But overall, nothing looking too terribly problematic in terms of distributions, at least given the fact that we're working with a relatively large sample of 220 individuals here. Okay, so nothing too big and concerning there. But what I want to do now is I want to go through and I want to take a look at my z-scores. So what I'm going to do is I'm going to go back to descriptives. I'm going to shut off save standardized values. I don't need z-scores on my z-scores. Don't need skew and kurtosis, because skew and kurtosis on my z-scores is going to be identical to skew and kurtosis on my raw variables. But what I am going to do is load up my standardized scores here and take a look at these. Okay, and remember, what I'm wanting to look for here is evidence for high standardized values that would suggest the potential for possible extreme cases. Okay, so if I'm looking at the min and max for my thwarted belongingness, my INQ belongingness, things are looking okay here. We got a low case, about a standard deviation and a little under a standard deviation and a half below this mean, about 2.6 standard deviations above. That's not too bad. NOS, we've got some low scores just falling a little over 3 standard deviations below, 2.9 standard deviations above. But again, that's not terrible given the fact that we're working with a pretty large sample. MSPSS scores, we've got a case that's getting close to 3.6 standard deviations below the mean, which we probably want to go through and take a look at and maybe flag these cases, right? So if we go back and I go to my MSPSS variable and I sort that, I see that what I've got a couple of cases that are exceeding that 3.29, which would be associated with a p equal 0.001 z. And so we've got a couple of cases here that we probably want to note. So we've got case 292 with an MSPSS value of 1.33, and that's falling about 3.6 standard deviations below. Case 333 has an MSPSS score of 1.58, and that's about 3.4 standard deviations below the mean. Right? So if we go back up and we take a look and reorient ourselves with what the average for the sample is. So average for the sample for MSPSS is about 5.6. So these are a couple of individuals who are reporting very low levels of social support relative to the rest of the sample. Okay. Now, is it possible that people could report very low levels of perceived support? Absolutely, right? So we don't necessarily worry. I'm not necessarily concerned that these are cases that are impossible within my sample, but we do want to note that these are, at least in the univariate distributions, cases that are associated with very large magnitude z-scores, and then sort of noticing that, yeah, this, if average is about 5.6, is that what we said? Yeah, about 5.6, a score 1.33, 1.58, that's pretty low for our output, right? And so this is going to be folks hanging out down here at the low end of our, at the low end of our MSPSS. Okay, so we want to go through and in our write-up note cases 292, 333, note the actual observed scores, and then the extremes or the z-scores associated with those two cases. Okay. We're not going to freak out yet. We're not too worried about this, but we are going to note this and see if these are cases that continue to come up down the road. Okay. So we've gone through, taken a look. Everything else looks pretty good in terms of potential extreme values. So what I want to do now is I'm going to go down through. So we've taken a look at accuracy, plausibility. We've looked at univariate distributions, extreme values, breakdown of our continuous variable. What I might want to do now is go through and take a look at my bivariate plots for my first order variables here. So I'm going to go down through and I'm going to go to my scatter dot plot, pop this up. Oops. Go down through here. And what I'm going to do is I'm going to order this up. So SPSS is my output, or my dependent variable. So I'm going to put that in there first. And then I'm going to include thwarted belongingness and my NOS score. And then I'm going to put participant sex here at the bottom, or at the last. And what this is going to do is in the graph, you can't have nonlinear relations with a dichotomous variable, but we can start to take a look at some variance assumptions there. So I'm going to drop these all into my scatter plot matrix. Going to hit paste. Okay. And then I'm going to go through and I'm going to run this. All right. So here's my plot. And I don't like this because it's not giving me a ton of information, or it's kind of hard to see. So I'm going to double click on this, open this up, and then click on my plot here. And I'm going to change this chart size. I like to hit it 460 and then hit apply. And that's going to make that chart just a little bit bigger. And I'm going to double click on my points. I'm going to change this around, reduce those down just so I can see a little bit more clearly what's going on. So we're going to close that. Okay. And then I'm going to go to elements. I'm going to hit fit line at total. And that's going to give me the linear relation between, or the best estimate of the linear association between my variables. And then what I'm going to do is I'm going to go to elements, or excuse me, options, show charts in the diagonal, and hit close. And this is going to give me just my univariate distributions to kind of remind me of what's going on. Okay. So I'm going to close out of that. And now I have a plot that I like, at least in terms of sort of seeing things a little bit more clearly here. So as I'm looking for my SPSS total here with my individual predictors, these relations all looking reasonably good. Looking at the spread of my scores across men and women, it's not looking like I'm getting huge levels of variability in one group and no variability in the other group. So I think we're doing okay here. So really, and if we go down through and take a look, this is just sort of the reflection of these graphs. Everything's looking pretty good in terms of not seeing any nonlinear associations and not seeing anything that looks like heteroscedastic associations, at least within the context of my bivariate plots. Okay, so variability looks pretty similar across my expected values here. Okay, we're not seeing weird fans, relatively comparable levels of variability across my levels of my dichotomous variable. So all in all, feeling pretty good about this. So in terms of concerns with linearity, homoscedasticity with respect to my bivariate plots, nothing that I'm seeing that's jumping out and making me concerned with these data. Okay. So to this point, we've gone through and taken a look at screening of our univariate distributions and our bivariate plots, extreme scores, and things like that. But what I want to do now is take a look at my assumptions of my residuals for my final model and my regression. And so what I'm going to do before I do that, remember that our model that we're looking at, we're going to regress SPSS scores onto NOS, INQ belonging, and then the interaction of NOS and belonging and sex and belonging. Okay. So to set this up in SPSS, I need to create some new variables, right? So I'm going to go compute. We call this centered sex equals my sex variable minus, and if I go back up and I take a look at the mean, now this isn't centering my my dichotomous variable is just so that I can, when I'm interpreting my conditional effects, I can just interpret these as controlling sex constant or controlling for variability attributable to sex. So we're just going to go through for the full model, and I see that my, well, whoops, I actually didn't get that. So here, let's go back up. And I'm going to go through. I don't need to center my outcome variable, so I'm just going to get my descriptives again. Okay, so my centered sex variable, I'm going to subtract the mean of 0.25. Okay, so that's going to be my centered sex variable. Then I'm going to create two more variables just to center NOS. Is going to be my NOS variable minus my mean is exactly 45. That's weird, but whatever. Okay, and then my centered belonging variable. Okay, so I take my INQ belonging, and I'm going to subtract a mean of 3.0436. Oops. 0.0436. Okay, I'm just pulling that from the mean here. All right, so I'm going to go through and I'm going to create these new variables. So here's my centered sex, centered NOS, centered belongingness. And then what I'm going to do is I'm going to go through and just check to make sure I did this right. So I'm going to look at descriptives for centered sex, centered NOS, and centered belongingness. Okay, so if I go through and I run my descriptives here, I'm saying that yes, my mean, so if I've centered these correctly, my mean should be very, very close to 0. So it's exactly reading exactly 0, 0 here, a little bit off here, but it's fine. It's sort of gotten it to, there's some rounding error going on there. So just a double check on my centered variables to make sure that I've done that correctly. Okay, so now what I need to do is I need to create a couple other variables for my interactions. Okay, so what I'm going to do is I'm going to create an interaction of sex times belongingness. Okay, because again, that was one of the interactions, and then NOS by belongingness. So I'm going to go sex by belonging is going to be equal to centered sex times centered belonging. And then here, create a variable sex times NOS. And this is going to be, paste that in there. Oops, no, not sex by NOS. NOS by belong, right? Sex by belong, NOS by belong. Yep, perfect. Okay, NOS by belong. Get rid of that. Centered NOS times centered belonging. All right, and so this gives me my two interaction variables: sex by belonging, NOS by belonging, NOS by belonging, sex by belonging. Perfect. Okay, so I'm going to go through, run this, and then this is going to give me my two interaction terms here. Okay, so now with this, we've got the variables that we need to run through and look at our full moderation model. And when we're looking for extreme values, multivariate outliers, and things along those lines, sometimes, not uncommonly, we get values that come up as contributing to high leverage or high influence points based on these multiplicative effects. So we want to make sure that we're including those when we're looking at our residual plot. Okay, so we're going to go to Analyze, regression linear. Okay, and our model, our perceived support is going to be our outcome, and we're going to include centered sex, centered NOS, and centered belonging in there, and then my two interaction terms. Okay. In terms of statistics, we're going to ask for the screening. We want collinearity diagnostics because we want to take a look at those tolerance and VIF values. Okay, so we're going to click and select that. And then for my plots, I want to get a plot of my predicted values against my residuals. Okay, so I'm going to put a predicted by residual plot here. I'm also going to get standardized plots, a histogram, and a normal probability plot for my residuals in SPSS. I'm going to click that and then go continue here. And I'm going to save my studentized deleted residuals, my cooks, and my leverage values. Okay. There's a lot of other things we could save, but we'll just go through and focus on those for now. So I'm going to hit continue there. And options, no, nothing there. Okay. So now I'm going to go through and I'm going to paste this out. All right. So what we're doing with this model is we're going to take a look at assumptions associated with the residuals of my model. Okay. Again, we're going to look for make sure that our residuals are normally distributed, that our residuals are homoscedastic, and that we don't have nonlinearity in our residuals. Okay, so that's what we're going to look at with our residual plots, and then we've also used this model to save discrepancies or our studentized residual values, our leverages, and our influence. Okay, so I'm going to go through, run the model. And for right now, I'm not going to be concerned about coefficients or anything like that. Because what I want to do first is take a look at my residuals. Okay, so if I take a look at my residuals here, one of the things that I like to do here is go through and, well, I just don't like those big dots. So I'm going to fill those up with something different and make them smaller. Just kind of, I think it lets me see better here. Okay, then we'll do that. And then I'm going to go y-axis reference line. And so I want to reference at 0 because the mean of my residuals by definition is going to be 0. So I'm going to hit apply just to give me so I can eyeball this and see that things should be above and below that center line here. So I'm going to go through and drop that. Okay. So what I'm seeing here is I'm not seeing any evidence of nonlinearity in my residuals. I don't have any weird things going on that would suggest some nonlinear relation that I'm not picking up. So linearity in my residuals looks pretty good. And the normality of my residuals also looks pretty good. I'm not seeing, just on average, things are pretty sparse down here, but I'm not seeing all of my residuals hanging out here clustered along this line. It looks like my residuals are for any value of my, or any level of my predicted value, my residuals look like they're pretty evenly distributed above and below my reference line here. So that's good. The one thing I am seeing is as we start to get down here, right, where we've got the most cases, because remember we have our outcome is our perceived social support, and most of our people are down here at the end reporting a lot of social support. Well, as what I'm seeing here is as my predicted value for social support starts to get increasingly large, particularly down here in this densely populated area, I'm starting to see some pretty noticeable reductions in the variability. So if I take a look at variability here at values just above a standardized score of 1, I'm seeing a lot less variability here and through sort of some of these values as maybe I am down here or even in the body here, right? Which suggests that I might have some potential problem with heteroskedasticity of my residuals. So my the distribution of my residuals across my predicted values is not homogeneous. It looks like and it doesn't really happen until we get down here towards the end. So as my predicted value increases, I'm starting to see a shrinkage in the variability of my error terms, which it's not the worst case of this that can happen, but it is something that we might probably want to note, that we may have some problems with potential violation of homoscedasticity of my residuals. Okay, so we're going to go through and maybe talk about that, and it's not bad. It's maybe an over-identification of a problem, but we'll at least identify this as something that's maybe tapering down as we get towards the end. Okay. So making a note of that, and then going up and also wanting to take a look at the histogram of our residuals, of our standardized residuals, is what SPSS gives us. So my standardized residuals, looks like I've got a low value here, but overall my residuals seem to be fairly normally distributed, so that's good. My PP plot of my residuals, you see some deviations probably associated with negative kurtosis, as we got kind of a peaked value here, but things are tracking that sort of diagonal line pretty good. So in terms of looking at these in terms of distribution of my residuals, not too worried about this necessarily. Okay, so based on my residual plot, my residuals appear to be linearly, there's no nonlinearity. I'm not seeing evidence of nonlinearity in my residuals. My residuals also appear to, both within predicted by my standardized residual plot, things look to be relatively normally distributed, which is looking similarly to what we're seeing there. The only thing, maybe a little bit of evidence of heteroscedasticity with a decreasing variability as my predicted value increases. Again, this probably isn't something we need to be too worried about, but a pattern that we might sort of at least note. It's just, and it looks like it's really mostly only happening right here at these really high values, but this is kind of where our greatest density of scores are at, so we might want to make a note of that. Okay, so that takes care of our residual plots. What we want to do now is take a look at the absolute value of our residuals. Remember that this is an evaluation of our discrepancies, okay? And our discrepancy measure that we've requested is our studentized residual here, okay? So what I'm going to do is I'm going to take my descriptives. Here, we'll just do this. I'm going to go down through, I'm going to go analyze, descriptives, and this time I'm going to look at my studentized deleted residuals. Okay. So remember that my studentized deleted residuals are going to be distributed as a t-distribution, and with 200 people in my sample, that t-distribution is close enough to a z-distribution that we can kind of interpret it that way. If I look at my min and my max values, I see I've got some higher residual values that are kind of big, but with this, what I'm really noticing here is a minimum minimum residual value of negative 4.87, right? So we're getting close to 5 standard deviations below the mean in terms of a residual. That's something we definitely want to take a look at, okay? So what I'm going to do is I'm going to go back to Analyze. I'm going to go to Descriptives, Explore. And this time what I want to do is I just want to get graphs for my studentized deleted residual here. Okay. I'm going to post that, go through and run my syntax. All right. And so what I'm seeing is some large residuals on the high end that are kind of following this continuous distribution. They're big, but they're not too concerning. But here I've got some cases that are falling really, really low. Okay. And if I take a look at my box plot here, it looks like case 291 and maybe 364 showing some issues of residuals that are starting to be pretty extreme. 290 isn't starting. That's for sure a large studentized residual. So if I go through and I take a look and I sort this, so these are my two cases here. So in terms of high discrepancy values, this one is obvious. This one is kind of borderline approaching, but but there's a big gap between that value and the next smallest value. And so probably want to identify case 291 and case 364 as associated with large negative studentized residuals. Okay. Remember our studentized deleted residual gives us an indication of the distance between the predicted value for that case in a model that case isn't included in versus the actual observed or predicted value for what we actually, or with the model, or excuse me, with that case in the model here. Okay, so if we go down through and we see again 291, 364, and identifying this, and again these negative residuals suggest that we have a case that the predicted value based on the model is a lot larger than the observed value. The observed value for this case for 291 for MSPSS is 2. And so this negative residual says that whatever the predicted value was in the model is way overestimated that relative to everything else. Okay. Same thing. We've got a lower value for 364, suggesting that again the model is overpredicted what we're actually seeing for that case. So these are probably the two cases out of all of these, and it's kind of capturing these two in the distribution. Everything else is part of a kind of this continuous histogram here. So we might flag these two as being potentially things to keep an eye on. Just because we have a large residual, remember, doesn't mean that we necessarily have a problem, but again, it's something to record and keep an eye on. Okay. So next thing we're going to do, the same thing, but we want to take a look at my discrepancy values. Okay, or excuse me, my leverage values. Okay, remember that leverage is our measure of multivariate outliers. So, and SPSS gives us centered leverage values. Okay, and remember that so our studentized deleted residuals are nice because it follows a t distribution, which is asymptotically close to a z distribution with large samples. My leverage values, though, kind of criteria for what we start to identify as maybe a large value starts to depend on how many variables we have in the model, how many people we have in the set, so on and so forth. And so remember that our centered leverages in SPSS gives us centered leverages. We're going to use a cut point of 3 times the number of predictors divided by n, which for these data, I have 5 predictor variables, my 3 base predictors, and my 2 interactions. So 3 times 5 divided by 220 is going to give me a value of 0.068. Okay, so what we're doing, we're going to look for leverage values that start to exceed 0.068 as things that might garner our attention. Okay. So we're going to go through and run our descriptives for our centered leverages. And again, with 0.068 as our cutoff, informal cutoff, we're definitely seeing cases that are exceeding that, right? So what we want to do is go through and plot these out. All right, and for our leverages plots, it's always going to be positively skewed, things bunched up around sort of low ends and then getting increasingly large. And so these are all, again, if 0.068 is our threshold, boy, all of this stuff technically is exceeding, conventional thresholds or potential recommended thresholds for things to maybe take a closer look at. But if I'm looking at I've got a cluster of scores out here that are definitely standing away from everything else, right? It looks like 233, 333, 222, 176. These are all cases that are looking to have pretty high leverage values, okay? If I go through and I take a look at my leverages and I sort those, again, if my cutoff is 0.086, or excuse me, 0.068, so I've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. So I've got 13 cases that are exceeding 3 times the average expected value, right? But I'm clearly not going to indiscriminately like wipe out 13 cases out of my total just because they happen to exceed some semi-arbitrary benchmark. So I want to be careful when I'm doing this. But if I'm going through and I'm taking a look, I'm seeing, again, these 4 cases here look like they're substantially larger than the others, at least in my plots. This collection of 4 cases up here is kind of doing, it's at least separated away. And so if I'm going to start looking at something, probably this set of cases is what I'm going to be most interested in. Okay. And so we've identified these as high leverage values. So these are potential multivariate outliers. Something weird in the combination of predictors is going on, right? But we just don't want to identify things based on a threshold. We want to kind of take a look and see what specific set of predictors is causing this to be a register as a semi-weird constellation of scores. Okay. So remember, based on recommendations from Dubachnik and Fidel, what we're going to do is we're going to hijack regression to kind of play around and see what cases or what variables are popping up in terms of contributing to these cases being potential multivariate outliers. So I'm going to go through and I'm going to go compute. I'm going to create a variable called MV1 equals to 0, period, EXE, okay. I'm going to create a set of 4 indicator variables for each of the 4 cases that I thought might be worth the most worth looking into. So I'm going to call that MV2, MV3, MV4. Okay, I'm going to run those. And what I've got now is a set of 4 variables that are just all 0. Okay, but what I'm going to do is I'm going to indicate, so this is my case with my leverage value, the largest leverage, second largest, third largest, whoops, fourth largest. Okay, so what I've done, MV1 identifies the case, my case with the highest leverage value versus everything else. This indicator identifies case with the second highest leverage against everything else, third highest against everything else, fourth highest against everything else. Okay, and what we want to do is we want to go through and take a look and see, okay, what specific variables are creating or associated with potential sort of combination, what combination of variables are maybe involved in identifying these cases as potential multivariate outliers. Okay, so I'm going to go to Analyze, Regression Linear, and this time instead of MSPSS, from our first case, I'm going to put this indicator from MV1, right? And so this is going to identify, tell me what cases are likely contributing to this case being weird in terms of leverage space. Okay, so I'm going to leave sex, NOS, belonging, so all my predictor variables are in there. But I'm going to go down through, and I don't care about collinearity here. I don't want any plots in this model. I don't need anything saved. I'm just going to be looking at so all I want to do is just look at my predictors here. Okay. Nope, I don't want scatter plot. It's trying to give that to me, so I'm going to just, there we go. Okay, so just a straight up regression model. So this is going to be my plot for, okay, so for my case with my largest residual or my largest leverage, that's this one right here. Okay, Case 233. What specific combination of variables are causing case 233 to register as a high leverage point? Okay. So if I go to my output and I look at my coefficients, it looks like some combination of sex, belongingness, and then the interaction of sex and belonging. Something about that combination of predictors is causing this to register as a multivariate outlier. Okay, so if I go through and I take a look, I'm seeing that, so I've got someone who's, in terms of sex one is male. Okay, so this person's maleness combined with a high levels of thwarted belongingness, so high levels of alienation. So if I look at belongingness, about a value of 6.4 is what this person is reporting. If I go up, let's see, just for reference here, I'm going to go and I'm just going to look at descriptives for my two continuous predictors here. Okay, so my average belonging score is 3, and this person has a 6.4, so I've got a combination of being male, really high feelings of alienation, and then something about the interaction of sex and belonging is also contributing to this being registering as a high leverage value. Okay, and that interaction is a little bit hard to make, sort of to know exactly what's going on, but something about the interaction of sex and thwarted belongingness is really sort of popping up and making this a weird case. Okay, so we want to record for case 233. We're seeing sex, belongingness, and sex by belongingness interaction as coming up as contributing to this being a strange value. But then we also have 3 other cases that, we also have 3 other cases that we want to take a look at that we identified as potentially strange. Okay, so I'm just going to run 3 other regressions with MV2 as the output, MV3, and MV4 is my outcome. Okay, so with MV2 as my outcome variable, at least in the way we're hijacking regression for this is going to tell me why 333 is coming up as weird. So if I run this, I see that 233 is being identified as strange, basically because this interaction of NOS and belonging is what's causing 333 to register as a multivariate outlier. Okay, and so here we've got a really high level of belonging, and my NOS, what's the average on my NOS? Is 45. Okay, so I've got this combination of high belonging and high NOS probably contributing to the strange interaction of NOS and belonging that really looks like it's causing this to come up weird. Okay, same thing. Take a look at my third variable, right? So this is going to be 222. 222 registering as a high leverage value due to the combination of sex, NOS, belongingness, and sex and belongingness. So we got 4 different factors going through here. So we've got someone who's male reporting high levels of thwarted belongingness, about average levels of NOS. Yeah, average levels of NOS, but then something about my belongingness. Yeah, so high levels of belongingness average levels of NOS, but then the interactions and then the interaction of sex and belonging coming up as being strange for this case. Okay. And then for my last one, this is going to be case 176. I mean, there's lots of other cases, but we'll just take a look and identify the four biggest ones. Here, going to be a combination of, looks to be low NOS scores, and then the interaction of NOS and belonging. So here, we're seeing low NOS scores. So this is sort of very low perceptions of or concern about the utilization of support resources, and then a very low INQ belonging score. So something involving low NOS and then the interaction of NOS belonging coming up and causing problems here. Okay, so if we're working with just an additive model where we're just able to go through and look at just main effects, right? It's easy to start to see exactly what's coming up as strange. Oh, I've got someone who is has really high levels of extroversion and reports really outgoing, but then also has high levels of social anxiety. It's a weird combination that we wouldn't expect to pop up, right? With your interaction terms, it starts to become a little more difficult to see exactly what's going on. But what we would want to do is note that for these four cases, of all the cases that are showing high leverage values, again exceeding maybe a conventional threshold of 0.068, these ones seem to be the most problematic. I want to write that down and sort of record what factors are contributing to these being strange cases. Okay, so that gives us our leverages or our multivariate outliers. Last thing we want to take a look at is our influence, right? Remember that influence is a combination of leverage and discrepancy. And the idea is being that these are cases that might have an undue, sort of high level of undue influence on your eventual model, okay? So for what we're going to do here is we're going to look at our measure of influence. Remember, as our Cook's D. So I'm going to look at my saved value for Cook's D here. And for Cook's D, sort of a threshold or a benchmark given as a guideline for Cook's D is going to be 4 divided by number of cases minus number of predictors minus 1. In our case, if we take 4 minus 220 minus 5 minus 1 is going to give us a value of 0.019. And so what we're going to be looking at is cases that exceed this Cook's D threshold of 0.019. So we're going to go through, run my Cooks, and again, 0.019 is my cut point. My max value of 0.107. So that's super high above what we would say maybe want to see based on conventional benchmarks, although conventional benchmarks we're always going to exceed conventional benchmarks because we're running behavioral science data and that's how it works. But we're going to go through and run this, look at my descriptives. So again, super skewed distribution here. It's kind of continuous, but all of this stuff over 0.06, that's starting to get really ugly out here. And so we got 1, 2, 3, 4, 5 cases that are really large, but there's a lot of cases that are going through and exceeding. If we go through and take a look at my Cooks, and I sort here, and if my cutoff I'm saying is 0.019, right? So cases, so 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Again, 13 cases that are coming up as being high potential influence values. Now, we don't want to just indiscriminately go through and get rid of cases because you end up with half the sample you started with if you're just doing that. But what we want to do is go through and identify cases that are maybe problematic or worth further looking into in terms of what are cases that are maybe most problematic given this. And so if I'm looking at my box plot here and my histogram, I'm kind of seeing a break happen here. And so maybe cases that are exceeding 0.06, so 333, 345, 292, 319, and 276. This one's really high up there in terms of being influential in terms of the model, right? And so we take a look at our cooks. Right, so these 4 cases want to go through and say, hey, these are additional cases that we might want to take a look at and to explore further in terms of potential impact, because not only are these big, these are really big, right? And so this is why it's important to plot, because if we're just using cut scores, then we got 13 cases to deal with. But really, this stuff is less concerning to me than these ones, given sort of the high levels that we've got going on here. Okay, so what I would do is go through and record these cases along with the observed leverage values, or excuse me, the long Cook's distance. And so what I've done is I've gone through and I've taken a look at discrepancies, leverages, and influence. But at this point, like, I'm trying to tie it all together and say, okay, what exactly are my most problematic cases, or that there are things that are coming up. And remember that one of the things that can be helpful with this is a combination, our leverage by residual plots. This can be helpful in terms of just giving us a graph for what's going on. So if I go to graph and I go to my scatter, but I just put in a regular scatter plot. And what I'm going to do is I'm going to request a plot of my centered leverages on my x-axis, and my studentized deleted residuals on my y's, right? And this is just to remember that influence is a combination of leverage and discrepancy. And so I'm just going to plot these out to see, am I seeing, of maybe the list of cases that I've identified to this, are there things that are coming up that are being obviously strange, right? So I'm going to go through and I'm going to plot this. And I'm not really seeing, I've got obvious cases that have, again, for our center leverage is 0.068. So anything kind of beyond this line, this whole collection of cases are things that at least objectively have high levels based on what we would expect from the model. But remember, for this combination plot, for this leverage by residual plot, what I'm really interested in, things happening up here in the upper right-hand corner and the lower right-hand corner. And so we've got a bunch of cases that are being weird in terms of predictor space, but it looks like they don't have super huge values for my studentized deleted residuals. So this additional plot isn't giving me too much extra. Now, if there are things way up here, way down here, that starts to sort of give me an idea, but there's really not anything that we're seeing. So our one case here that had a really massive residual is actually sort of not a terribly high leverage value, right? So the constellation of cases in terms of predictor space were fine. It was just we were way off base in terms of the prediction. This case that's super strange in terms of the combination of predictors, we're actually not doing that bad in terms of getting close to the observed value. So in this case, our combination plot, our leverage by residual plot, isn't giving us too much here. All right. But it can be hard sometimes to go through and pick up and make a determination, kind of put this together and say, all right, based on my screening, what are the values or what are the cases that I might be most interested in following up? What I've started to do with these is put together a little sheet to kind of help me keep track of what's going on, right? So here, as we were working through this, we found that case 292 and 333, both of those cases had high values for extreme values. low outcome scores, low social support scores. So these were kind of coming up as strange in terms of our outcome. 291 and 364. These were cases that came up as having large studentized residuals, right? So this is the expected value for that case for a model that doesn't include that case versus the actual value that was observed for that case, right? And so what we're seeing here is a couple of, particularly here, this is a massive residual, but 291 isn't coming up as problematic anywhere else, right? In terms of leverages, again, this is our measure of multivariate outlier. We got 333, 233, 222, and 176, all being registered as high leverage values. This one because of the interaction of NOS and belonging. This because of sex, belonging, and the interaction. Sex, NOS, belonging, the interaction, and then the interaction here. And then our high influence values, right? These were all the cases that had high cooks. And then our leverage by residual plot that we didn't see much there in terms of pointing us at specific cases. Remember that for this, if you double click on this and go to elements, say show data labels, what it'll do is it'll label the position of that point in your set, right? These aren't subject numbers. These are sort of the order this case occurs in. And so 187, that one way out here at the end, is case 233, right? And yeah, that was the case with the my largest leverage value here, okay? So this is how we can go through an SPSS, label these cases. We're actually not getting anything that's giving us too much more information, right? But if I go through and I take a look at overall, what are the cases if I had to go through and do, and I probably would want to do some follow-up to start to see what happens, what's the impact of this case on my model? Probably 333 would be a case that I might want to follow up with and look at a little bit more. This is a sort of a weird low value for reported support, which is plausible and likely a member of our target population. People can have low levels of support, right? But this is just low, pretty low relative to the sample. And it's also coming up as having a high leverage value. And remember that leverage is just working with the predictor variables. So this has a weird interaction in terms of predictive space and also coming up as one of our high influence values. So I might take a look at that. And I also might take a look at 276, just because that had a really obscene influence value. So I might want to go through, and if I wanted to follow up and look at the impact, and I probably should, of these cases on my solution, what I might do is I might run the solution with the set minus case 333 and see what that does to my predictors. If it doesn't change anything, then I'm fine with it, that's good. But if things start to jump around a whole lot, whether or not I have one case in or one case out, particularly in a case of 220 observations, if I see substantial changes in a coefficient based on whether or not I have one or two people in or out of the model, that starts to be concerning to me on the stability of that effect and the confidence that I can have that what I've found or not found is actually a real thing, right? So these might be the first couple of cases that I would play around and take a look at, just because, one, this one's kind of doubled down on a number of things. This one just has a really high influence value. I may take a look at 292 just because you're seeing a pretty high influence value combined with that really, really low score on my outcome. So these would maybe be cases I might follow up in sort of further investigation, specifically looking at the specific impact on my solution. Okay, so that kind of takes us through some considerations there. Last thing I want to do, take a look at collinearity issues. We haven't done that yet, so I'm going to go down through to correlate. Look at bivariate correlations between sort of all of my predictors here. We're just going to worry about my first order effects. I'm not going to include interactions because I expect those to be pretty highly correlated among correlated variables. But if I go through and I take a look at my correlations, I'm seeing some strong correlations here between my outcome, my MSPSS, not super related to participant sex, but there's pretty strong negative correlation with thwarted belongingness. So as my feelings of alienation go up, my perceived support goes down. As I start to get increasingly anxious and sort of hesitant about utilizing support, my reported perceived support goes down. The correlation of thwarted belongingness and willingness to utilize support resources is pretty high correlation here, but again, nothing that would suggest problems, at least in the bivariate case, of clear multicollinearity to the point that I couldn't run my model. So as long as these variables make conceptual theoretical sense, we can probably move forward, although we should note that they are pretty highly correlated predictors, at least with belongingness and NOS. Okay. Last thing I want to do is way back at the top when we ran the full regression model to get our residuals and all that stuff. We had also requested collinearity diagnostics. I'm just going to go through because I don't want to scroll through my output and see that again. So I'm just going to run the whole model again and taking a look at my collinearity diagnostics. Okay. So again, for NOS and belonging, right? Those were the two cases or the two variables that I saw had a pretty high bivariate correlation. This is popping up in terms of my tolerance levels. Remember that tolerance value of 1 indicates no collinearity or sort of independent effects. Anything below 0.1 is maybe problematic, but anything that would get even close to that is going to be problematic. So we're seeing correlations here, but things that are acceptable. Again, our VIF, our general benchmarks is a VIF of 10. But if you got anything even like a light year away from that, you should start to become concerned. But here, VIFs of 1.80 and 1.89, probably not anything too much to worry about in terms of our collinearity stuff. So, yep, we have highly correlated predictors, at least in terms of our NOS and our INQ belonging scores, but for the most part, nothing too concerning. Okay, so that works us through our screening for our multiplicative model or our moderation model. What we could do in terms of a write-up, and I'll make sure that you all have this, again, working through our standard structure, accuracy, plausibility, things are looking fine there. Missing values for INQ belongingness on cases 216 and 301. Case 189, missing for MSPSS, so we're sort of noting that there. Univariate distributions, describing box plots, histograms, and things along those lines. Here, making sure to make note of our ratio of our dichotomous indicator. Again, about a 3-to-1 split, but acceptable for what we're doing here. Univariate outliers or extreme values. I like this. Noting nothing much for INQ or NOS, but MSPSS having some stuff come up. Bivariate associations, linearity on homoscedasticity of our scatter plots are looking okay. Residual distributions, this is looking fine except for potential violations of homogeneity. My discrepancy is going through talking about my discrepancies. Leverage values here. Influence values going through and talking about here. And then my multicollinearity diagnostics going on with this. So in terms of recommendations for this set, 3 cases with high values for missing values for INQ, belongingness, and MSPSS. Some potential extreme values on my outcome variable, violations of evidence of heteroscedastic residuals, maybe, and then high values for discrepancy, leverage, and influence that came up. Okay, so here in the recommendations, we're saying missing this probably isn't a problem. It's just a couple of cases, so I'm not too worried about it. Noting that we do have some problems with potential heteroscedastic residuals. Our specific pattern here with decreasing variability in residuals with increasing predicted values suggests that we could have some inflated standard errors. And if our standard errors are too big, it's going to make our tests for our individual predictors too small. It's probably not a huge issue, but something that you might note. And then going through and identifying that we did have a lot of cases come up in terms of discrepancy, leverage, and influence. Cases 333 and 176, maybe with the 276, not 176, and 276 as potentially the greatest scrutiny. Recommend looking at sort of the impact of these on your overall coefficients. And so I actually did, independent of this video, go through and take a look at what happens if we start eliminating and running the model without, say, 333 and 276. And you do start to see that this makes, particularly this coefficient for, in the first model, in the overall model with the full set, these are your coefficients here for all of your effects and your p-values. If we drop case number 333, what we get is this interaction effect goes away. The p-value is 0.151, If this entire interaction goes away, is contingent on one case, I start to worry about whether or not I've identified anything that's sort of really true and stable here. By contrast, if I eliminate case number 176, which was the other one, now all of a sudden that p-value jumps up to 0.109. And if I go through and systematically delete others, basically this interaction just flip-flops back and forth, which suggests to me that this interaction is very, very unstable and contingent. In order for this to come up as meeting conventional thresholds for interpretation, I have to have a certain small set of one or two cases in the mix in order for that to come up, which tells me that this is not a stable interaction. This is not something that I would put any money on replicating in future studies. And so really sort of up to you in terms of how you would go through. And if I go through and I eliminate all 13 cases that came up as potentially weird, this interaction doesn't come up. Again, suggesting that this is probably not a stable effect within this model. Now, there's some concerns of going through and sort of cherry picking what cases you include or what you don't. But if you're doing responsible data analyses, hopefully your biggest concern is to what extent, if I'm going to publish these data, are other people going to be able to replicate? Is this something that's real and consistent? And based on our screening, I think that this effect that's just right at p equal 0.05 doesn't end up being, we don't have there conclusively. I don't think that there's strong evidence of a dependency of belongingness on perceived support across levels of NOS. So in terms of our write-up, we'd say, hey, we want to go through and take a look at these. Also, we could explore potential other alternative methods for looking at to address potential violations of homoscedasticity. So this could be regression with robust standard errors, WLS, weighted least squares. Weighted least squares probably isn't a great solution, given that we really need probably really large samples for that, but a couple things that we could do. So I'll make sure that you have this example, this write-up, and I'll give you the data that we use for this if you want to go through and take a look. But hopefully this helps sort of wrap your head around screening for your multiplicative models. Let me know if you have any questions, and good luck with this.